Okay, hi. Uh, as was said, I am Michael Hatridge. It's a pleasure to be here today. Does this, no? Oh, the internet is hard. Oh, good. If only I could advance my slides. Okay, we'll just do it this way. I'm very grateful to the organizers, especially Mazyar, who emailed me and said, would you like to come talk about your favorite thing ever? And I said, yeah, I mean, I'm doing it right now, but I'll come do it at Stanford also. I am a superconducting person. My photons are real. But amusingly, as we have missed all day, the parametric couplings are actually what's fake in this system. And I would encourage folks in the back, folks in the front, to stop me as I go along. I tend to do better with something to react against. So yeah, the parametric couplings are fake. A real parametric coupling is like, imagine you take an inductor and you shunt it with some mechanically compliant capacitor. I don't have these things in real life, but I kind of imagine that I do, because like when I was young and working for Michel Devoret on parametric couplings, I was like, what's a parametric coupling? And he's like, it's this, which is that, you reach in with your hand, you apply some force on that compliant capacitor. And if you force it up and down, you can change the capacitance of the object. You change the parameter of the system. That's where the name is supposed to mean. And so the good features here, right, is it relies on susceptibility to motion or change in the system, which means it's inactive if not driven. Controls that don't turn off are the worst. It needs to power some process of interest, for instance, amplification in this linear LC oscillator here. And so, to do that, typically what makes it parametric, not resonant, is that the drive here is far off resonance. So in this particular example, will be something like 2 omega naught to make a phase sensitive amplifier, right? So that's a real parametric process. The way we misuse the term, I thought in superconducting circuits, but I'm starting to come to think also in optics as well, doesn't really mean that at all. So here's like a real parametric oscillator in our laboratory. Okay, a real circuit that does fake parametric oscillations in our laboratory. We can't make mechanically compliant capacitors so easily. We really like to make like nonlinear inductors. We kind of take most of the real parametric stuff. It's inactive if not driven. It powers some process of interest. The drive is typically far off resonance. But to understand the stuff I'm talking about today, you have to let go of the fact that it's a real parameter. And I'm going to just say there's some general non-rotating term in the Hamiltonian. That's where the turning off is going to come from, something that doesn't conserve energy. And I'm going to use it to build a lower order interaction term that does conserve energy, and then I'm going to be off and running. Maybe you're like, why is he bothering with this? In superconducting circuits, we do both of these. And it gets really confusing, even for someone who does it for a living, when someone is talking about, let's call this one parametric, because that's the term we're all using, and let's call this one real parametric. When you get confused about which kind you're talking about, all the orders of your Hamiltonian are off, all the symmetries of your circuit are off, it just really makes a mess. So to make this fake kind of parametric coupling, how would we do that, right? So if I pretended I was a theorist, I'd say what I really want is some term like phi A, phi B, phi C. These are the fluxes in 3 inductors. And I'm going to rewrite this in terms of raising and lowering operators, A plus A dagger, B plus B dagger, C plus C dagger, right? And then I'm going to form modes using these 3 inductors. They can be harmonic oscillators, they can be qubits, they can be, choose your own adventure here. And so then the trick here now is that if omega A, omega B, omega C are all rather different, then this term here, A plus A dagger, B plus B dagger, C plus C dagger, does like not a damn thing. Okay, so great. I've accomplished nothing, which is what I set out to do. And then now I'm going to look into this Hamiltonian and say, I wish I had, for instance, AB plus A dagger, B dagger, right? That's one of our friendly Hamiltonians. That's the Hamiltonian for 2 harmonic oscillators that gives you phase preserving gain. If it's 2 transmons or 2 qubits, it gives you what's called a B-swap gate. And so I'm going to activate that by driving the C mode. And all it really needs to be is that I'm not accidentally on resonance with the C mode. As long as the C mode is somewhere else, somewhere far away from my drive, then I can take the stiff pump approximation, replace this operator with the letter, and I'm going to get effective two-body interaction whose strength is determined by G3. This is the thing that Amir was telling us about, times the voltage here, or the root photon number, basically how hard I'm driving the system. This simple Hamiltonian contains all of these combinations for all three modes. It also contains difference drives, so a B dagger. So that's going to be photon swapping or conversion, or if it's two qubits, you're going to get I swap, or if it's two cavities, you're going to get like what's called a swap gate, or what Rob Sholkoff and his crew call a beam splitter interaction. And again, the only difference here now is that I'm going to drive at the difference frequency to now make this satisfy the rotating wave. And so this is kind of where I entered the story as a postdoc, using these terms to build parametric amplifiers. That's a particular case of parametric couplings where you have low Q systems that are designed to not hang on to their photons. We learned early on, trying to give these to other groups, that all amplifiers have to come in a gold box. So we gold plated the box. And I know that there's tons of physical implementations of this, but this is the kind of like story that I'm trying to set up to tell you today. Okay, so as I've been sitting here all day today struggling with basic vocabulary, I realized that the superconducting people in the room are kind of not explaining some of our key obsessions. So the first thing is that superconducting circuits are Mexican food. So I'm from South Texas. You guys in the South Bay here have some pretty decent Mexican food. What you know is that the chalupa, the taco to the enchilada is just like, a trivial transformation of the same basic ingredients. That's actually what superconducting circuits is. We have the inductor, the capacitor. Sometimes we get them all together at once as like an actual, resonator. And then we have one nonlinear element with the Josephson junction. The two awesome and terrible things about the Josephson junction is that number one, it's too damn nonlinear. And number two, like it's super flexible. And these are going to be the things that basically I struggle with for the rest of the talk. So it has this cosinusoidal energy term in the Hamiltonian, where phi again is like the superconducting order parameter across the junction. If I just trivially expand that out as a Taylor series, the quadratic term tells me that this is like an inductor. Then I get a quartic term, a hexic term, an octic term. All of these are big enough and scary enough to do things even when I don't want them to. And part of the flexibility that's a little bit confusing in these circuits is that we make these junctions routinely in the lab over something like an energy range of 10 to the 4, between the biggest junctions in the paramps and the smallest junctions in the qubits. Any questions so far? Okay. One example of how the junctions are too nonlinear is that like the most famous commodity transmon qubit these days, the transmon, actually comes from taking a Josephson junction, which is a charged qubit and way too nonlinear, and just trying really hard to crush the nonlinearity, to just crush it until there's almost nothing left. When we do that, the mistake we make here is that we take the rotating wave approximation and we truncate off all the higher order terms, and then we say it's like a harmonic oscillator plus some self-Kerr term here, and that's going to separate the energy levels from each other by something like 150, 200 megahertz on a qubit frequency of like 3, 5, 6, 7 gigahertz. I will show you later in the talk why this is both removing some of the fun and a general bad idea. So in terms of three-wave mixing, which I guess is a Chi 2, good. Everything is synthetic, right? So we end up coming up with favorite strategies for building these same three-wave mixing elements over and over again. This is the one I cut my teeth on. It's called the linearly shunted Josephson ring modulator. It is nice because it does that exact A plus A dagger, B plus B dagger, C plus C dagger kind of three-wave mixing. It has the purest Hamiltonian. It is a pain in the butt because the spatial modes are currents left to right and top to bottom, which are not so bad. But then you have this like flexing mode. And this circuit only wants to connect three things to three things. So it's kind of gone extinct over the COVID. Like everybody quietly stopped making them. These days, we typically make these two things on the right across the field. Michelle is not here yet, good. This is an RF squid. It is a linear inductor shunting a Josephson junction. There's a thing called the squid handbook. which has like a whole philosophy of life around the RF squid and the DZC squid. I have to offer the disclaimer, lest you tell on me to Michelle later. I don't mean any of that crap. I just mean a linear inductor shunting a junction. And the neat thing about this, and the same thing that you see here, which is basically 4 of these things fused together, is that when you flux bias this circuit, you can get a pure 3-wave leading order nonlinearity. So 3-wave is the leading thing, and then no 4, and you get 5, and then no 6, and then you get 7, and so on and so forth. This is nice, like an amplifier. So here's an amplifier RF squid. It's like a 6 microamp junction. This is like maybe 6 or 8 microns tall. When you want a low inductance device, quite easy to have just a few microns of shunt across the junction to make your device. When you want to build something qubity or in a 3D architecture where you need many nanohenries of inductance, so again, like something like thousands of times larger, it's much easier to make the equivalent of this inductor here out of 3 big Josephson junctions. So this is kind of like acting like an array to dilute the nonlinearity and get back this sort of left-right asymmetry that allows us to create a 3-wave coupling as a dominant nonlinearity in a circuit. So these are basically what we use to do everything in our laboratory these days. We were told to, not give you the full hour of talk. And then I realized also, Irfan left, so nobody but me in the room likes to build microwave parametric amplifiers. This is kind of where the terms and a lot of my thinking in this area originated. The things we build these days are something like this. It's just a shunting capacitor, a coupling capacitor, shunting capacitor, and then those RF squids I showed you before. If I try to summarize for you some of the key features that you might go look at if you're curious later, and I gave a bunch of literature at the bottom right. So paramps are classical objects that like quantum fields happen to. And this is really important because what we've learned sort of painfully over probably way too long a period is that those truncated Hamiltonians, like I showed you before, like that it's A plus A dagger cubed. Like you just have to let go of that. You have to take the full nonlinearity of the circuit. Because it's basically classical, we're operating in some correspondence limit here. We can just take the hats off and do the full untruncated time domain numerics. And that's the design tool we use in our laboratory for everything. So full, ugly, gross things. There's no Hamiltonian terms anymore. There's just sort of big loops in computers that we then like feed in and run heuristics on to figure out how to divide the devices. It's not super fun, but the awesome thing is that it works. We do typically use arraying as a clutch. So these little line-looking things here are going to tend to be 10 or 20 RF squids in a row in our devices these days. We use this to sort of build a stiffer system. So when you do this, you make n RF squids in a row. You cut the 3rd order nonlinearity by n, but then you cut the 5th by n cubed and the 7th by n5. So you really can sort of make the 2 nonlinear thing I told you was a problem start to act like a pure 3-wave coupler. It's a neat strategy. I'll show you a graph in a second that kind of everybody's been following it. It has this brutal feature that for every dB of saturation power that we gain, it costs us a dB of pump power. So that means when I make the amplifiers these days that are 30 to 40 dB more powerful than the old amplifiers, the pump is trying to catch my fridge on fire. There are some ways around this. You can kind of build floppy in the right way circuits, and we do have a recent publication on that group. The idea is sort of that you can use the right nonlinearity to build a system that kind of straightens out as you pump it harder instead of getting crooked. I think that's maybe not a thing we should talk about today. The feature that kind of leads into Michelle's talk tomorrow, however, is that for many years, when you try to read out transmon qubits or fluxonium qubits with high fidelity, the claim would be that if we only had a better paramp, we could read these things out better and get the 9s of fidelity that we needed. Now, the amplifiers we build and use in the lab can tolerate about 100 times more photons than the qubits. And so Michelle's actually going to tell you about how they have different parametric problems in the qubits that you can now see because we got the parametric problems in the amplifier sort of straightened out. These are not very high Q objects. They typically have a gain bandwidth product. So if you use 20 dB gain, you get about 1/10 of the bandwidth that you start with. We partly solve that by the fact that like the Q of this thing is like 4. But then we can also so my laboratory has one hammer and it's called parametric couplings, and we literally just use it on everything. So it should not surprise you that we can increase the bandwidth by using more parametric couplings. You can actually apply the gain and the conversion couplings that I showed you simultaneously to engineer, for instance, a system with neutral feedback. We call it the GC amplifier for gain and conversion. You can actually imbalance them where the conversion is stronger and even make a matched amplifier by combining multiple of these drives together. And then the other thing that people are doing very successfully these days is building filter-based broadening circuits. The only thing that these amplifiers continue to be not great at is directionality. So there is a way to use yet more parametric couplings among, for instance, a triangle of modes or 4 modes. The requirements are like 3 to 6 parametric couplings. And those are awesome devices. We've built them in our laboratory. In practice, they tend to be like a bridge too far to be the kind of amplifier you could give to a lab that's not obsessed with parametric couplings. So with the bulk of the talk, oh, sorry, here's that slide. So here's pump power, and then here is saturation power. And you'll notice that they're scaled sort of 1-to-1. And so the really best amplifiers, here's kind of the wiener ones. Here's some of the ones we've been making in the lab these days. The best one is the kinetic conductance one in terms of the cavity-based amplifiers. But you'll notice that every dB is basically costing you a dB. So it's not a thing to be like, you don't want to build an amplifier with 100 times more saturation power than you really need, or you're going to have 100 times more heating problems in your fridge than you'd like. And we, as people who build these devices, we have a lot of conversations that go like this. Like, dear Hat Lab, we would like an amplifier like this. It's like, no, you don't. If we gave it to you, it just complained that the pump is too strong. So there is kind of a little bit of a question in the field where you really need to build just enough paramp just to satisfy your needs.
Where does the pump go? Where does it go? Like, I mean,
Reflects off.
I mean, like, could you just, recirculate it or something? I mean, because, the thing isn't lossy really, aside from the gain, right?
You can build a higher Q input circuit at the cost of stiffness. There's kind of you'll notice that there's a huge amount of scatter here. There's 2 pieces of this that's laid out in David Pecker's new paper that we collaborated on. There's one piece which is trivially just like, how good is the pump at getting to the node of your circuit with the snails on it? We can do much better on that sort of for free. Then there's how much can the amplifier consume before it sort of gives out? And that's the part that's really like that we, for instance, would not be able to fix by putting some oscillator there, because you need the stiffness of that pump. If we built a real mode there, then its fluctuations would start to impinge themselves on the amplifier, and your amplifier gain would go like this, and you would lose your quantum efficiency. Again, we thought this 0.1 number was kind of important, but it turns out that it's just this stiffness argument. So the theoretical bound of this is something like 10% or 15%. So we can do something like a couple order magnitude better, basically by saying, what tends to happen is that you have these static curves and static 5th orders and static 3rd orders in your system. But then when you pump it, you pick up these dynamic 3rd, 4th, and 5th orders in the system. If they have the same sign, they reinforce each other, and you have a problem. If the static one and the dynamic one oppose each other, then the system kind of, like I say, straightens itself out as you pump harder. So in the new paper just came out on the archive, they will show you like an RS squid design like we showed you like on the last slide, but instead of being very stiff, very just 3-wave coupling and nothing else, it has designer 3, 4, 5, 6-wave coupling, where each one kind of kicks in and then your gain kind of oscillates, but kind of within the 1 dB bound of sort of usual saturation. So I think that's the way that you do better on this. Yeah, thank you for the question. Any others? Any basic terms I should define before I'm off to the races? Yeah, what I mean is like how many line widths is the drive outside the mode that I'm driving? So there's this C mode that I showed you before. The stiffness is basically going to be, if it's 2 line widths outside the mode, I really have quantum fluctuations in the trajectory that the mode is actually following. And that C that I took an expectation value out of is now an uncertain number. If I'm like 500 line widths outside the mode that I'm driving, then like it's just a thing where when I turn the pulse on, it responds instantaneously with the pulse, and it turns on and off instantaneously with the pulse. So for me, stiffness, we could call it like delta over kappa and probably tell you like 10 is okay, 100 is great, 3 is no good. Yeah, like, yeah. That's right. Yeah. You want the pump to be, again, you want everything about this device to be classical. Yep. Basically, if it's easy to pump, it's a bad amplifier. So what are we in the business of in our laboratory here today? So we kind of want to do like what we call Hamiltonian engineering with these parametric couplings. And so the idea is like Maziar might come by to visit, or we might read some paper, and they would say, if you only have this interaction term, then you can build your qubit or your sensor or your widget. And that's really the business we quite consciously trying to get into. And so the formula we're going to follow is say, okay, like that blue thing is the effective dynamics I want. Then as long as I have a higher order term here, so like these EF and G terms are sort of extra waves in the system, then I can pump them to satisfy energy conservation for the first 4 parts, right? And there's probably like lots of choices of different pump frequencies I can apply to these modes. And then that will make a parametric coupling, and I'll use it to do, I don't know, whatever I want to do. There's a lot, as Irfan showed you, I think Dave will show you more, of like parametric controls in the superconducting world that are built on this formula. It all works. The problem is they're not usually clean. By which I mean that you activate multiple parametric drives that you don't want to, you shift your mode into some other mode and have some collision, right? And so when we try to figure out like what's the best way to go about this, there's a bunch of sort of problems, and I'm going to try to talk to you about some of them today. So the first one is that the relative speeds of these different parametric processes are unclear. So, GM is the prefactor, it times the number of photons, in this EF and G modes are going to tell me the speed in this example. The problem is, in terms of photon numbers, I can't put much more than 1 or 2 photons typically in a mode these days. And the GM kind of falls as I go from 6 to 8, but not very fast. So it's a little bit ambiguous, like, am I better off using more pump photons and fewer dynamics photons or not? Activating unwanted terms is not that uncommon. I will show you graphs with like 10 parametric couplings on them in a second here. And then, of course, in systems where I allow myself to have even order terms, every damn thing moves around. Not only the modes of the system, but the parametric susceptibilities move around, and it gets really hard to avoid collisions. And so our strategy for how we build the circuits in our laboratory are typically use 3-wave couplings. We're going to weakly hybridize the coupler, if you like, with our qubits or cavities or whatever they are, to minimize the sort of cross-Kerr type terms in the system. And then the third piece, which maybe not everybody else does, is to use the absolutely lowest frequency pumps that we can get away with. So, if I can solve a tie with a pump that's lower in frequency, I'm going to just select that. Yeah. Yeah, let me answer that on the next slide. So this is an example of how we're going to build a gate. So imagine that these are 2 high Q cavities, if you like, or they could be 2 qubits, 2 transmons, if you like, or they could even be, it turns out to work just fine if they're 1 transmon and one cavity. So the G over deltas here are between the coupler and the mode. So I eat a cost of every G over delta that couples outside the coupler. If it stays inside the coupler, I don't. So for instance, the trade-off here might be to use the 3rd order nonlinearity of the snail versus the 5th. And so, here, if I want to make the I-swap gate family some continuous series of gates in the I-swap, then I'm just going to drive this snail now in between these 2 A and B modes at the difference of the 2. The rate of the gate is G3. So that's the thing we want to make, maybe big. I don't know yet. G over delta squared, which is going to kind of tell me how many cross-Kerr and type errors I have. So it might be nice to be small. And then S is the thing that I would like to be very big, because I would like to compensate for these 2 terms by just driving the hell out of it. In paramps, we take G3s that are of like the 100 kilohertz order, and we do pump them up to like hundreds of megahertz. So in the right system, these can be sort of huge pumps. And then, the things here to remember is that the prefactor scales as G over delta squared in this example, and that the gate rate goes as S. So this is the usual bad kind of Rabi, right? Where to have twice as much gate, you need 4 times as much power. And then just for people, maybe everybody in the audience but me already knew this, but when I started making gates between qubits, I-swap is a medium crappy gate. It is I think it's a perfect entangler, but it's like the worst perfect entangler. Turns out root I-swap is one of the best gates. in terms of its ability to generate sort of a random gate set on demand. And we've actually done a lot of work in the system. We started partnering with Alex Jones and his computer science student, Alex McKinney, Evan McKinney, Alex Jones. It turns out ISWAP in this system is really the best. You know, I told you before we could combine gate and conversion together to make cool new kinds of parametric amplifiers. You can also do this to build cool kinds of gates. So if we play both couplings at the same time, in that system I just showed you, we can make C0 gates, we can make B gates, which are like the best gate. But it turns out that when we look at both the sort of the computer science times the physical constraints, ISWAP just kind of wins every single time. So this is the kind of modules that we're building. So we're learning how to scale up. We have an Army program where we're supposed to build something like 10 or 20 transmons. And all we're doing here is sort of taking what we would call a module to put one snail in the middle of 4 transmon qubits. It's going to infect all of the qubits with cross 3-wave couplings. And then what we're going to do is now, you know, the parametric couplings don't care what your frequency is, but they care intensely what your difference is. So we're going to lay out these 6 potential couplings here so that they don't collide in frequency. There are some subharmonic drives we need to watch out for. There's actually something like 10 or 20 potential parametric couplings that we know to watch out for in the system, but it turns out we can lay them all out in frequency space. And then again, you'll notice that we put all the parametric susceptibilities very low frequency. And then we actually use a low pass filter on the drive line so we can drive like crazy down here to activate the gates while protecting the lifetimes of the snails and qubits up above. And so this is a pretty successful system. And again, the question though is how fast can we go, right? So in every, as Dave keeps saying, like, you know, you should just have more cooperativity, you should just have more speed, you should just have faster gates. In the system right now, when we kind of make optimal trade-offs or what we think are optimal trade-offs, we can make the ISWAP gates go as fast as something like 36 nanoseconds, which is a pretty good number for superconducting systems. But of course, then the reviewer at the journal you send it to is like, yeah, but why isn't it 10? And so that's kind of like the heart of my talk today. Why isn't it 10? And so what I want to spend the rest of the time telling you about is the speed limits of parametric gates. So we have been collecting a series of examples in my laboratory of how the gates can go wrong. One of the easiest ways to make your parametric couple go wrong is you just drive it too hard. So this graph here is looking at the snail in the center of our module, actually by swapping its light out to a qubit to study it. And then you can see here that here green means you're in the ground state of the snail. And you would just like to apply a parametric drive away from any process of interest, so nothing should happen. So this plot should just be a green block. And it stays green, it turns out, until you get to some very particular sort of slowly varying threshold, and then it goes nuts. And this wiggles here is probably the attenuations of our line. We did a lot of work to make sure that heating and stuff are not problems in our system. This is actually the low pass filter kicking in. You can see that suddenly you can't kill the snail anymore, but you're not heating the fridge or having any other kinds of problems. And so we call this death. However, we just heard a talk where somebody said something about the damage limit in, right? Is the word damage limit said? Yeah, that means like you're actually cooking your circuit. This is like the kind of death you come back from, no problem. Just like wait 100 microseconds, your snail will have calmed down from whatever Fox state you've put it into. So not that kind of death. Yeah, like 3, 10, depends. I don't know if I knew this. That like figuring out why and where that number is happening is what I'm going to talk to you about in this talk, in the remainder of the talk. And so on my plot here, you know, I've got drive strength on the vertical axis, hybridization on the horizontal axis. Every one of these lines is a family of faster and faster gates. I just want to be top right of the plot. I would have the fewest like cross current problems if I was on the left axis, but I can't go there because I go straight up into death. And so then you decide to hybridize stronger and drive weaker, and then you run into a different set of problems. So again, the circuits are too nonlinear. There are 5th and 7th and 9th order interactions. As you drive the system stronger, they tend to get stronger faster than the 3-wave one. And so here's a neat example of a gate between, I don't know, qubit 1 and 4 in the module. As you're driving harder, it's going faster and faster and faster. And then it stops going faster and actually starts going slower again. So this is like in the papers by people like Petrescu and stuff. It turns out like what you think is a three-wave coupling that goes on forever is some sort of Bessel function that as you sweep out, you start to see where it drops away. And so the one that we've been making progress on the laboratory today is actually this one about the maximum power a coupler can take. And I thought it was useful to talk about today because if we wanted to go on some adventure together of building some circuit, this is the biggest parameter I don't understand right now, like how hard I can drive before it dies. Yeah. Yeah. If I build a system like at this coordinate, I will hit the slowdown and then die. If I build it at the other coordinate, I will hit the death and never see the slowdown. So like these are both processes that can happen as I play with my G over deltas and my pump strength. I'm going to move between which one of them happens first. Like this one's a coherent process, right? This is predictable from your Hamiltonian just by like adding in the terms that you wish you didn't have. The death one, I guess now we kind of know how to predict it, but this is only in the last couple months that we started to figure this out. I want to reach neither. I just want to go faster. That's something you could explain with your. Okay, if I've learned anything from like 15 years of quantum information is that your gates are never fast enough. So if I know this trade-off and I know the death trade-off, I'm going to try to play them against each other and push myself as far to the right as I can. And then I'm going to try to design a new coupler element that hoists off one of them a little bit longer to keep going for more gate speed. I don't think we ever get to like stop pushing for more gate speed, do we? Okay, so the way I'm going to show you about these speed limits and how it works, this is a Crazy Science Friday project in my lab, you know, the thing at the end of the week where everybody's tired and you're like, maybe we should think about something new today. And this came out of some dumb remark on my part, where we love parametric couplings in my lab. We use them for so much stuff. And the students, you know, were saying, yeah, Michael, but what about the single qubit gates? They're not parametric. And it's like, well, there's got to be a way. And there is. So if you take the transmon Hamiltonian I showed you before and you just rewrite it before you take the rotating wave approximation, you have A dagger plus A4. And if you have your sort of parametric thinking hat on, you realize there's a term in there like A dagger and then 3 A's. And so what this says, if you read it in words, is if you drive the transmon at 1/3 of its frequency, you can make it Rabi. Something like this here. And so we did this. You know, there are a few things to keep in mind. Now, when you retake the Hamiltonian, knowing that you want to preserve this term, you know, you get back a start shift. It's going to be quite big because we want to drive fast. You get back the anharmonicity, and now you get back this drive now that goes as eta cubed, where eta is like the effective power of your drive. So this is going to be like normal Rabi driving, except it uses 3 pump photons. And you're going to have to keep tracking the qubit because it's going to start shift. It's going to try to move out from under you as you drive it. This is the system. It's completely generic and boring. We just grab some random transmon in the laboratory. So we work in circuit QED, which means that every transmon is partnered with some readout cavity. You don't need to really worry about that. It's just the way that we read it out. The key feature here is that once again, like borrowed from my snail couplers, you're going to see a low pass filter here where the qubit is drivable at 1/3 of its frequency, but you cannot access the GE frequency of the transmon. Resonantly, it's protected by the low pass filter. Some of the reasons this is not just a Crazy Science Friday experiment is that as you get better and better transmons, you have to more and more weakly decouple them from the environment to perturb their lifetime, right? But then you have to drive harder just to get the same damn amount of light in. And then you start to heat your fridge. There is actually a really big heating problem in the kind of cryostats that we're using. So these reflective filters are really nice. We can take attenuators out of the fridge. And so, you know, this might actually be something that a company like IBM wants to consider when they have thousands of fridges to worry about, qubits to worry about in the cryostat. Okay, so the paper was published on the archive like a year ago. The reviewers were not kind. They said they wanted more 9, so we rebuilt the system. And something really neat happened. So there's the Hamiltonian again. Here now is frequency that I'm driving at. So this is like something like a 4 gigahertz transmon. I think it's like 3.8 something. Here's the drive amplitude. As I drive harder and harder, it moves down to lower and lower frequencies, and Rabi's faster and faster. If I plot for you the Rabi rate, which is just this cubic dependence versus the Stark shift, basically there's one free parameter here that fits this, so everything is working as expected. I would note with you that the Stark shift is huge. It's actually bigger than anharmonicity. And the drive rates we can get to are on the order of 50 megahertz now. These are now, these are very competitive pulses. These are basically as fast as anybody drives their transmon. So that's really cool. But then you'll notice that something bad is, like, I've truncated the graph very deliberately here because something bad is about to happen. If I zoom out, it looks like this. This is the same thing I showed you for a snail. In fact, this death thing is in every parametric coupling we've looked at. Again, if I move over to one side here, there's no parametric process as I just drive straight up. Then the qubit dies. This qubit had really good readout. So what I'm showing you here is single shot monitoring of the bottom, I guess it's 6 states, G, E, F, H, I, and then past J, we can't really tell anymore. Because one of the questions we've been asking ourselves for a while is, like, is this heating from G to E? Is it from G to F? And in fact, what we find in the data is that the qubit is just like, it's gone. It seems to show up a little bit in I, seems to have some weight in J+, but it really prefers none of these states. It's just completely scrambled among, let's say, maybe 10 or something like this states in the manifold. That turned out to be one of our important hints when we tried to unravel this. The other thing I would show you is that this process here is, do I have my labels? Yeah. This is an 8th wave process. I told you that the processes don't really die off in a comfortable way. This is 6 pump photons driving a 2 photon transition in the transmon. So we're really cool. This is all brand new data taken in the last, I think, month. Maybe it's 6 weeks now. If I now prefer the excited state, I see some more drives. I see EF over 3. I see this is EH over 6. There was accidentally some cavity to qubit transition that was very nearby, luckily just out of the way. And then again, you see that the threshold moves lower. See, lower. And then F state is lower still. And so what we did, I guess, starting in August, is we sat down with Jens Koch, we've been working with this theory on for a while, and then with Alexander Bley, and we really tried to say, like, this is the simplest system we can build. A transmon is much simpler than a snail. There's not lots of modes in the system. Really, there's just the transmon, and we're killing it by driving it on itself. Can we really stop sort of being confused and figure this out? And so one of the first things that they decided to do, their shields are unfortunately being murdered by the mute box, is kind of treat the transmon like we've been treating the parametric amplifier. So this is quantum, so we can't take the hats off. But let's imagine that, like, we are very afraid that we don't understand the system. So let's just do full numerics. Let's do time domain here, so no frequency domain shortcuts. And then let's just do like 20-something states for the transmon and 10 for the cavity, and then we'll crunch on it for a week and we'll average over gate charge. And then when we do that, we generate plots that look like this. They look encouragingly almost exactly like the data that I showed. And they share some of the features. So here's preparing the ground state. And they also see, you can kind of, I don't know how good the contrast is. Can you see like a little bit of color up here? So there's like a few states that are more likely than others. But again, the full numerics also says that the transmon has just like left the building and is not in any sensible or reasonable state that you might expect, like G, E, F, or even H. And again, this was really gross because so Alexandre's group is really an expert on this Floquet theory. If you're going up to like the 11th and the 15th state of the transmon, these states are very charge dependent. So not only are these numerics very expensive, you have to average over many, many gate charges because there's no longer any reason to assume that your transmon is insensitive to the gate. So they did this for us. And then luckily it turns out that this is not the only thing they can do. So oh, you like my plot. The other thing you can do is Floquet analysis. Again, you can basically go into the driven frame of the transmon and you can say, what are the steady states, and basically try to track them. As Irfan told you, these things are quasi-periodic, so you kind of need to unfold this monster. And when you do so, you can look at, for instance, just a few levels, like the ground and the excited state. And this is just a heuristic, but basically, like, it kind of looks okay, except like maybe something has gone horribly wrong here, right? And for the excited, Yep. The excited state, something has gone horribly wrong there. Vice versa. Yeah, gray is the ground state. And so if we just take this heuristic, let me just skip this because I'm running low on time. This is the data on the left. Very Princess Bride here. Blue is like mostly dead, red is all dead. And we just like now lay them. This is now the full numerics of the colors here. And then the little dots are the Floquet. You'll notice that there's like really awesome correspondence. And the only fit parameter we're using here is we're matching the fringes to make sure that we're applying sort of the same strength of drive. And so this is like orders of magnitude better than we've ever been able to sort of understand or predict the speed limits of the kind of driving that we're doing in our system. So this is, we're just not talking publicly about this. We have now a paper in this infamous journal in preparation. But we're really excited. And in terms of like this workshop, or when one thinks about parametric journeys, you know, we have like these new tools like Floquet. What it's telling us is a little bit confusing still. So when your theorist friends say the word chaos to each other, then they have a fight. One of them will say like, there is no chaos in quantum systems, right? There's a thing. And then the other one will say, oh, but there, you know, and then you sit quietly in the corner as the experimentalist until it's over. Something bad is happening here. It's a different kind of collision that Michelle will tell you about tomorrow. It is some kind of like the qubit loses its mind and starts to chaotically explore its space. What flavor of chaos it is, how it scales, you know, sort of almost anything about what next, we don't really know. I forgot to tell you that it catches all three of the states really nicely. So it doesn't just catch the ground state death, it catches the excited state, the F state death. What we want to do with this new tool now, however, is to really, again, it's kind of like our amplifiers. It's like a heuristic based on a lot of computer math. So you don't get equations of motion, you don't get nice analytical stuff anymore. But we can start to ask bigger questions, or the basic questions, let's say, that I can't answer right now. Like, is a bigger anharmonicity transmon going to run a better subharmonic gate or a worse one? Because we have the gate sort of speed moving and we have chaos moving, and maybe they don't move together, right? If snails can be adapted into this Floquet theory, you know, and start to predict their data, then I can go back to those early plots and then sort of make the trade-offs that I'd like to make, or select something as Maziar suggested, where this sort of Bessel function slowdown is the ultimate limit that I have to accept. And I think that we're going to find, you know, I don't know if Floquet will carry us through all of our problems, but these kind of explorations are going to be how we sort of build bigger and better quantum processors and really try to make progress. And at least, you know, my personal obsession with doing everything with parametric drives. Okay, I want to say thank you. And then the Mingkang Shah is the student who took all the data that I showed you today. Thank you very much.
All right, so we got about 10, 12 minutes for discussion. Any questions to start us off?
Yeah, I guess this is maybe alluding to your comment at the end, but your point is that this is distinct from these measurement-induced state transition superconducting circuits, or because I guess to me the signature looks somewhat similar, I guess, right? I drive my readout strong enough.
So mist is a Michel term that just means something bad happens. So Alexandre Blay has a different term called ionization, or boinkage, as he now wants us to call it. Huh? Jens calls it boinkage. Alexandre calls it ionization. Okay, so if you look at the paper by, I can always remember it because I keep thinking Three Musketeers. There's a paper by Dumas, right? Yeah, that one, this one. They will tell you that generally speaking, when you put your cavity, when you drive a qubit above its resonant frequency, a transmon, you're going to get these kind of collisions. So Michelle tomorrow is going to show you those kinds of things. They are like a specific parametric process where you cross with like the 7th level. It's a very coherent kind of bad thing that can go wrong. Below the cavity, there's this kind of entry to chaos phenomenon. But how it looks, it seems to be a function of how far detuned we are. So like nobody puts their cavity down at 1 gigahertz for a 5 gigahertz transmon, right? So I will tell you that like, even though this is all Floquet and all Alexandre, like this, this kink heuristic is not in the papers, right? So this is like a new heuristic to try to look at the fact that at least qualitatively, these things look different than the existing examples.
But at some level, would you say they all reduce to just driving strongly? And so then you start to have all these shifts on all these modes, and you just have some high order mixing process that couples two modes together.
No, no, that's the one above the cavity. Chaos is different. So these particular transitions care about where the other transition is. So with, like gate charge moving away or something, you might find that the transition goes away and comes back and goes away and comes back. Like chaos, at least like we used to build these things called bifurcation amplifiers. And we've studied like Duffing physics and Josephson circuits before. Chaos doesn't care about particular levels. You will also notice, maybe this is not the best example, but like for the snail, like we're scanning over a huge, this is actually many octaves of frequency, right? From like 0.3 to 3. And you'll notice that like the threshold, except for some oscillations, doesn't change by more than like a factor of 2. So this is not a special frequency kind of phenomenon. So I don't really have evidence to say like that's why I took this data. We took this 6-state data because we were hoping that like 5 would light up. And we'd say, see, it's a transition to 5. And there are examples where that kind of stuff happens, but this is not that. And it's not clear to me that chaos cares about fine features in the same way that those collisions do. It's all the fact that you drive a Josephson junction too hard and it snaps. But we need to like, sort out all the different details, the different parameter regimes, and sort of predict what's going to happen.
Just a quick question about the simulation. So are these, is the loss important in these simulations?
Yeah, right. Flow K is a weird theory in that it has no resonator and it has no loss. And the numerics here have no loss. So it's not, this is not the world's best transmon, but this pulse is only 100 nanoseconds. So we've also varied this experimentally from like 100 microseconds to like 3 microseconds. These thresholds don't really depend on the length of the pulse. So they don't seem to be very susceptible to lifetimes. Yeah, right. But we don't put in 1 megahertz or something. Yeah. Right, but the numerics are straight Schrodinger's equation, no loss. The full numerics, the colors. What do you mean?
Like, so if you look at the 16 states there,
yeah.
When you're up in the depth, you don't have your probability.
No, it still adds to 1. Well, this is the simulation with 20 times 10. So I guess it's across all 300 adds up to 1. I'm only showing you the bottom 15 with the Fock state 0 in the cavity. But yes, if I summed over all the 20 times 10, it should sum to 1. Don't know. I don't know. Right? Clearly something very bad is happening. And I don't know if 50 would make a difference or something.
Something like trace out the cavity receptor. Like, is it localized?
What do you mean, is it localized?
You draw the wave package. Basically, the over many eigenstates. Is it localized?
Oh, like, does it look like some kind of wave packet or something? Jens has a different version of the theory where the answer is yes. But it's like jumped over, like away from the jumped way away from the ground state one and is some very complicated wave packet made up of almost all of these things. So there may be something like that going on.
I have kind of an open-ended question. Like it seems, so this system is super complicated and like
No, it's the simplest one that exists in circuit QED.
Okay, right. But it sounds like it's not super easy to say like, okay, if you want really fast parametric rates, like choose this amplitude and choose this detuning.
Oh.
So yeah, so what's, if you were to, this is again an open-ended question, but like if there was advice on like how to choose an optimum. Is it to do this really beefy simulation and just do it once and then try to interpret the results, or is it apply flow K analysis to your system? Or
Well, obviously, we're going to do the flow K because it's like day on a cluster and not week on a cluster or whatever. It's not quite laptop level, but it's not very gross. So we're going to run it against flow K. I will tell you that we've already built this transmon again with like half the anharmonicity. We see all these same features, and we're then trying to fit it again, right? So you can imagine that now what we're going to do, I don't know, in my lab, we typically try to do like make it really bad, make it really good. So we're going to try to design a coupler that's like the worst, dumbest idea coupler that flow K says like explodes when you sneeze on it. And then we're going to try to like do the very best coupler that stands up to the drive forever, and try to do some A/B testing to see how valid either flow K is or numerics are for. The problem is even the numerics again don't really work for the snail. You know those 3 junctions?
Hmm.
Like one of the many assumptions we're telling ourselves is that they all oscillate as delta over 3. Now, when I start to add the other modes, if mixing among those modes is important in the way it dies, then I got to capture those. So then I can do 20 by 20 by 20.
Yeah.
I don't think I'm going to survive, right?
yeah, but it sounds like basically the first step in your design process is use this flow K analysis and sort of try to
Yeah,
understand. the
if we're
system a little
lucky in this low drive parameter regime where everything is much lower than any mode in the system, if the, let's say, or entry to chaos kind of phenomenon has some like, let's say, simple monotonic scaling where like more anharmonicity goes roughly linearly or roughly quadratically, then I can apply this to the process and say I should be either very low or very high. I don't know. It's pretty exciting though that at least I can start to like, try to test those things
Yeah,
with the correspondence that we have here.
yeah, I agree. Thanks.
But yeah, I don't know, like, should your snail have G3 of 1 megahertz or 100? I don't know. And the problem is also that the transmon's def doesn't care what you're doing it. I'm using this particular process, right, where the scaling is voltage cubed. If I were to drive some other process on the same transmon, like a beam splitter, like Rob used to use qubits between his cavities. Now, the scaling of the gate versus the scaling of chaos will be very different. So you may have to ask like if it's a Tuesday, and I've been a good person and I'm applying a 5-photon drive, what's the best circuit? It may not be any more general, than very specific constraints about frequency and order. Okay.
Was that add inductive shunts and enough of it to your transmon?
Yeah. Yeah, that's okay. So, these still die.
Yeah, but
They just die in a less spectacular way. They start to be downside pendulums and they become upside pendulums. So they won't like do the chaos explosion thing, which is good. But like my G3 will just stop getting bigger and they get smaller again.
you'll have that dynamic of the Bessel function that you'll have.
Sure.
That's something that you don't need flow simulations to see it. You can calculate perturbatively and you know what's going
Right.
on.
Yeah. Right. So then if that gives me a faster gate, then yeah, I'll use that. Yeah.
One more question?
Yeah. So for the particular case of these drive coordinates we explored, there was not a strong, like, interesting dependence on gate charge. They all kind of looked like this. For the above the cavity collision ones, I think you will start to light up specific ones, but we're not, that's qubit readout where the cavity is above the qubit. This is a different shenanigan. It's just driving your transmon low.
And then maybe another question, for the case where you do have like the ionization from measurement, do you think that that's still going to have this chaos behavior, but it's just happening after the coherent like state swapping?
Okay, let's be clear. The ionization is in a flow K theory that has no cavity. So I think it's really good to recast. So these papers all say they're about measurement, right? But flow K has no cavity. What those papers are really saying is the following drives will kill your transmon. Now you apply like one level of gloss on top is, and that drive is a measurement thing. Or I'm saying, and that drive is a parametric subharmonic gate. But let's not say that it's a measurement induced whatever. It's just a drive that transmon can't hang on to. In flow K, there is no cavity. So I think it's more useful to say, these are drives you can't put on a transmon. In the measurement process, don't put these drives on the transmon. In the gate process, don't put these drives on the transmon. See how it's a little bit different statement?
Yeah. Thanks.
All right, so I think let's go ahead and thank the speaker one last time. So we'll have a coffee break for 15 minutes, and then let's all meet back here at 4 p.m. sharp for the next talk.